a map T, which is E from F, which is okay, T, a map T from F, E to F, a linear T from E to F is bounded if so it's a definition, there exists a constant C, okay, must be positive obviously, such that the norm of TF can be estimated by C times of norm of F and G. Okay, and obviously this must be in capital F, and this must be E for all F. E. So this is what that we define F to be T to be a bounded operator. ठीक है जी? ठीक है जी? Is it making sense? So a map is bounded if there exists a C such that this inequality holds. Okay?
Sir, linearity implies boundedness. मतलब एक और additional condition.
Okay.
Additional condition.
No, this is rubbish because differential operator is linear, but it's not bounded actually. So don't believe everything that I say. Don't believe everything that I say. Because I was confusing something that is called continuity and boundedness basically. So this is something else. Anyway, so here is the definition of boundedness. Okay. Of operator. So now I am defining basically L of E to F. So it is the set of all linear maps, linear bounded. T is linear and bounded. Okay. From E into F actually, okay. Then we can check that this guy is a vector space, okay, by this is scalar multiplication and addition, all right. And this is an important space actually, okay. It's a vector space. And it has and I can define a notion of normality. Alright. Okay, so if F is maybe quick remark actually, that if the first remark is if F is same as E, then we're going to denote it as L of E only, calligraphic L of E. So it's the set of all linear operators from E to E. And second is that if F is K, then this set of all linear maps from E into K is basically what you call E star. So it's the dual of E actually. Okay? And the element of duals are also called tensors sometimes. Okay. Tensors of certain specific ranks. Okay, I'm not getting into that discussion. Okay, so tensors are actually multilinear maps or linear maps. Anyway, is it making sense? Okay. So how much time do we have? 15 minutes. So let's do some examples. Okay. So probably it's time to prove a little lemma. Okay. So here's a little lemma which will kind of allow us to define the norm of all this. And in other words, what we can do is that we can turn this vector space into a normed space. Okay. So in other words, I can have a notion of norm. So this lemma kind of justifies the existence of basically that particular norm. Okay, so here's a lemma. It says that a linear map T from E into F is bounded if and only if, okay, a norm of T, okay, which I am defining as, maybe some people call it a norm of T, or some people call it norm of T in on space LEF, okay, with respect to LEF. This, which is kind of a norm on LE, on this space actually. Okay, can be defined as supremum of the TF, where the norm of F is less than or equal to what? 1 is fine. Okay. So what does this lemma is telling you? If you have a bounded linear operator, then you can talk about its size. And that size would be that take the supremums of TFs over those vectors, okay, whose norm is less than or equal to 1. Okay, so there's a reason behind it, that why we need a norm of less than or equal to 1. Not getting into it, as we have time to discuss it later. Okay, is finite. And so here's a proof. Here's a proof of it. So what we need to do. So this side, assume that it's bounded. So if it is bounded, what should be true? So it should be true that okay. Some people also define this as norm of F equal to 1. Less than or equal to 1 or equal to 1. It doesn't matter. Okay. So all right. I'll write that as a remark. So let me stick with that at the moment. Less than or equal to 1. But then I'll show you that there are a number of ways to write. Okay. So different people use different kind of notation to write the norm of an operator. But they all are equivalent actually. They are not different. Okay. So the first part is that if T is bounded and linear, then I know that there exists a C such that norm of TF is less than or equal to C times of norm of F. And obviously this norm is in F
And this is an E.
and this is in E actually. Agreed? And why do you think that it follows this above inequality from it? Just think about it. Is there a way to get it? Why it must be finite? So here's a trick. So that's a number, I can divide both sides by this number, okay? and I can, so if this will be divided, I can plug in that number inside norm. Okay. So what I'm going to have norm of TF and F divided by norm of F. Okay. Because T is linear, so I can insert it basically inside as well. Okay. And in F, this must be less than or equal to C. Now, what you can say about this guy? So it must have a unit size actually. So therefore, I was saying that you can even put a equal sign here actually as well. Okay. So this is true for all F. This is true for all F. Small f in the capital F. Okay. No, small f in the E actually. Okay. Less than or equal to C. So if this is true for this, okay, then it must be true for the supremum as well. Okay. It must be true for the
supremum भी वो finite भी होगा.
Supremum भी finite भी होगा. And it must be true for the supremum. First question, why does the supremum exist?
C belongs to D.
What do we mean by bounded? So forget about this. Why the supremum of this, such kind of things exist? It exists because T is a bounded operator, and so it's like all of these numbers have some basically bound. So there must be a supremum by least of a bound property. Okay, this is certainly something what we call trivial. Okay, and now if this is the case, then isn't that sufficient basically? Okay. Isn't that sufficient to show that the supremum of those G's from F, from E, such that norm of P of G, where the norm of G is less than or equal to 1 or exactly equal to 1, is less than or equal to C and hence finite. Why this guy must be less than or equal to C? Because this will become, so I'm saying, so I have replaced this by G actually, okay, roughly. Okay, so I have replaced this by G. So if T of G for such G's is less than or equal to C for all, then the supremum is also going to be bounded by C, because the supremum is the least bound and this is the bound actually. So it must be true as well. And if this is the case, then this guy must be finite. R, the norm of P is finite. Okay? Converse is trivial. I don't need to tell you. Okay? Maybe, but okay, it's not that trivial, but you have to think carefully, because this guy is showing you that the supremum of TF of those F is finite, for which the norm of F is less than or equal to 1. But you have to show it for the general one actually. Because just think about it, for the boundedness you need what? You need norm of TF less than or equal to C times of norm of F for all F and E. So you have to be careful. Okay. So it's trivial, but it's not as trivial actually. So you have to. I don't know that whether you can go backward or not. I think you can go backward.
Sir, Chota was by definition T is bounded and linear if that exists.
You know.
So take
it's always fun Okay, to prove the trivial things. Okay, the trivial things are not, that trivial actually. Sometimes. Okay.
We should prove.
Alright, so let me finish this up on a quick remark. Quick remark. Okay. That norm of t, okay, norm of t can be written in several ways. So one of the ways is supremum of tf divided by, that norm of f less than or equal to 1. That's one way to write it. There is another way to write it, and that is that the supremum of tf such that magnitude of f is 1. That's another way to write it. And there is another way to write it, okay, that the supremum of f which are not to 0, and you simply compare the norm of tf divided by the norm of f. Okay. And my claim is that all three are given. So maybe it would be fun to verify them as well. Okay? Verify them. Okay? And finally, you have to also verify that with this norm, this guy becomes
non-displaced.
F भी वेक्टर स्पेस है, नॉर्म भी है ऑलरेडी assumed है.
आपको स्केलर किससे मल्टीप्लाई करना है? E and F has a common field actually, which is going to be K. तो या तो दोनों R होंगे या तो दोनों C.
दोनों में वो क्लास
दोनों ही जो है आपके पास क्या होंगे, कॉमन होंगे.
सेकंड इक्विवेलेंट
Supremum of norm of TF divided by the norm of F of those F which are not 0. ठीक है, तीनों equivalent है. So you have to prove this. Examples भी चलिए next class में हम discuss करेंगे. यार ये classes जो है, एक तो ये जो class रह गई है, इसे adjust करें कहीं, because सारा हमारा जो है